Yeah.
I mean, that's pretty big.
We're supposed to, I also.
For the couple.
Washington is, but it also rains a lot.
We're the next test.
Right, Massachusetts might be pretty good.
I almost fell off on stage.
But it doesn't have much else.
They got Harvard Canadians.
They do, they have Harvard and MIT.
Like all the way. Take you up, and I'm like, see.
I'm pretty sure so like we're the only city where they can open universities when like if we've established a country.
Whichever state has the best food scene.
Then I was
Like, I just want to eat like that.
Wisconsin.
No, you can find like the gas, it's like delay and just out.
Guys,
state
what?
like-
What?
Police bureau.
All right, if you can turn to page 21. We talked about Taylor series and a Maclaurin series, but we're going to review this. And this is an important formula that we're going to have to need to know for our quiz next Wednesday. So if you guys can keep your formulas worksheet handy, we're going to refer back to this as we after we get through page 21. Yeah, that was available on Wednesday, so if you didn't grab one on Wednesday, you can grab it now.
Did we get it there? There's.
Yeah, I'll bring the story tomorrow. I'll tell you on the next. Unfortunately. Oh, no. I can't because they don't want to talk to me. What? I'm thinking it doesn't matter. Apparently they
All right, so if a function, guys. Okay, so if a function has derivatives of all orders at x equals c, then a Taylor series may be formed that is equal to the function for the many common functions. So we know that the first two terms, basically, the way we build Taylor series is we're gathering information from the function that we want to imitate or to emulate, and we're pulling the y value, the slope, the concavity, the third derivative, the fourth derivative. And so to build that, we're always going to start off by building out the point slope, the linear equation. So it's always y sub 0 plus m times x minus x of 1. So the first portion is always going to just be its own thing. It's going to be just a linear expression. And after that, then we can start building out the rest of the formula, which is the second derivative evaluated at c over 2 factorial x minus c squared plus, and then the next one would be the third derivative evaluated at c over 3 factorial x minus c cubed. Now, the general term would be this, which is the nth derivative evaluated at c over n factorial x minus c to the n. Now, I know that this matches better with anything starting with 2. Technically, this still also applies with these two. It's just that you have zeros and ones involved, and it's just easier, cleaner to just think of it as its own separate thing, linear equation, and then the form takes on a better shape after, with 2 factorial on, because these don't show up because you have 1 factorial, you have 0 factorial. and it's not worth the time to set those up. But this is our formula that is building out each of the terms. And if we were to strip away replacing the c with 0, then it'll become the Maclaurin series. Maclaurin series will be f of 0 plus f prime of 0 times x. There's no need for x minus c because the c are all going to be 0. So replace the c with 0, replace the c with 0, and that's your Maclaurin. Okay, we do need to know we do need to memorize the Maclaurin series for e to the x, cosine, sine, 1 over 1 plus x, and also I have a couple more it's going to be on your review sheet that we're going to be working towards to memorize. Since we could build it from scratch, but if we build everything from scratch, it would take too long, and we just don't have that kind of time on the AP exam. So for the common ones, we need to have those memorized, and I'll talk about how I go about formulating those terms. But let's just see if we can build out one or two of these. So let's build out the Maclaurin series for e to the x, and then for sine of x, and just so you can see what it looks like to build it from scratch, and then we'll talk about working towards memorizing them. So Maclaurin series for e to the x, we're going to gather all the information that we need from the order pairs at 0 and all the derivatives at 0 as well. So our function is e to the x. Let's just go ahead and find everything. Let's go to the third derivative. Okay, so f prime of x. Well, the nice thing about e to the x is what's the derivative of e to the x? Yeah, so that's going to be nice, right? All the derivatives are just going to be e to the x. So if I were to evaluate each of them at 0, it will give me the same thing every time. F of 0 is e to the 0, which is 1. F prime of 1 is e to the 0 is also 1. F double prime of 1 is also 1. The third derivative, evaluate 1, is also 1. Okay. So let me write out Maclaurin series for our problem here. It's always going to be f of 0 plus the slope times x minus 0, but I'm just going to put x, and then f double prime of 0 over 2 factorial x squared, and then f third derivative evaluate at 0 over 3 factorial x cubed. So all we need to do is to fill in the f of 0, f prime of 0, f double prime of 0, and the third derivative evaluate at 0 with 1s, because these are all the values that we found. So all we're doing is we're just replacing these terms here. So the polynomial version of e to the x is just 1 plus 1x plus 1 over 2 x squared, or x squared over 2 factorial, plus 1 over 3 factorial times x cubed, or x cubed over 3 factorial. And you can kind of see the pattern build out. Yes. Oh, sorry, my bad. You're right. All these should be zeros. Thanks. And the e to the 0 is 1. Sorry, I got these mixed up. All these are 1s, but yeah, you're right. Maclaurin series, it should be all evaluated at 0. All right, we'll do the same thing for sine. For sine, we're going to have f of x is sine of x. We're going to let's find everything up to the fourth derivative. After that, we can find the derivative evaluated at zeros for all of the derivatives. And then put it into the same formula here for Maclaurin series. So sine's derivative is cosine, cosine's derivative is negative sine sine's derivative is negative cosine, back to sine. I'm finding all the derivatives at 0. And then it's f of 0 plus f prime of 0 times x. F double prime of 0 over 2 factorial x squared. Then plus the third derivative value at 0 over 3 factorial times x cubed. And if you see, every other derivative is 0. So basically, it's going to wipe out every other degree. So basically, it's only going to be the odd degrees that's going to show up. It's going to be 1x minus x cubed over 3 factorial. Plus, sorry, this should be plus x to the 5th over 5 factorial. All right. Any questions so far? Okay, if you can pick up, let's shift over to that worksheet that you picked up. And I'm going to go through the key version of this. And this is what your quiz will look like on Wednesday. It's going to look exactly like this. You just have to be able to fill in all these spaces. The only thing that's going to be different is number 5. Number 5 is just a problem that you have to go through and find your interval of convergence. So you're just going to get a different variation of number 5. But let me talk through the key version, and then we can practice, or I can talk about the patterns of it, and then hopefully that will help you work towards memorizing these forms. So first is it's just the alternating series remainder theorem. We talked about how if we want to find if it's an alternating series and if the series is converging, then we know that we can figure out how accurate our partial sum is by looking at the first unused term. So yeah, so guys, for now, don't fill out that blank sheet. Use the blank sheet later for practice. Of course, I'm going to have some additional blank sheets, but for now, if you can just follow with me on the key page, just go to that second page where the key is. Yeah, so in your handout, yeah, just follow with me on the key, and then we can talk about, you guys can practice writing this out later. Okay, Maclaurin series, we talked about that, where Maclaurin and Taylor series are virtually the same thing. It's just that Taylor series is a bit more adaptable to other centers, but your Maclaurin series is going to be centered at 0. So if you can memorize Taylor series, you can just strip away the C's into zeros, and that will get you your Maclaurin. So this is what I'm looking for here. Including the terms up to the nth term. So I want you to show me the first 4 terms, and then also the general term. So Now, let's talk about sine, cosine, and e to the x, just some common patterns here. Now, sine is labeled as an odd function. If you think back on sine and cosine, it's an odd function. And, the fact that sine is an odd function is helpful in their Maclaurin and expansion because all the degrees are odd. So I think that's a nice connection there. And then cosine is an even function because if you look at a cosine function, you can fold the cosine over the y-axis and and it's going to overlap each other. And that is helpful because cosine has all even degrees, right? Even 1 is an even degree because it's x to the 0 power. And then sine and cosine all have alternating signs. So you start with positive, then negative, then positive, then negative. And there's factorials involved here. So 3 over 3 factorial, 5 over 5 factorial, 7 over 7 factorial. And you also have to write the general term as well. The way you create an odd number is you do either 2n plus 1 or 2n minus 1. Basically, the 2n is going to ensure you a positive number, and then you're adding 1 to it, which is always going to force it to be negative. So 2n plus 1, 2n plus 1. Now, you may be asking, wait, does it matter the summation in terms of where the n starts? You don't have to specify where the n starts, meaning that on the AP exam, there may be different variations of this. You may have 2n minus 1, 2n minus 1 factorial. As long as you have a general term that works for either starting at 1 or 0, they will accept either. Okay, so there are different variations of your general term, but I would just go ahead and just memorize this one because if you do minus 1, then you may have to adjust this exponent so that the signs will match up. But just to let you know, you could have different variations of the general term if you start at 0 or 1. Sometimes starting at 0 can create you an easier looking version. Sometimes starting at 1 can create the easier looking version, but you don't have to specify whether you start at 1 or 0. You can just write out the form and AP exam will, College Board will accept either one as long as you have a valid version. Okay. Now, what's the relationship between sine and cosine derivative-wise? Cosine is the what of sine? Derivative, right? Sine's derivative is cosine. So technically, if I find the derivative of this, it should bring me down to this. Okay, so let's just try that. I just want to just kind of show you this here. What's the derivative of x? 1. What's the derivative of x cubed over 3 factorial? So I would bring the 3 down, right? So 3x squared over 3 factorial. What does this turn into? If I were to clean this up. X squared over, well, what can I do with the 3 and 3 factorial? I can cancel out the 3's. I'm just left with what? 2 factorial. So there it is, x squared over 2 factorial. Right, so it's nice to see that, okay, if I have sine, if I forget cosine's formula, I can just find the derivative and get to the next term. Same thing here. If I bring down the 5 down, the 5's will cancel out. I'm left with 5x to the 4th. The 5 cancels out. I'm left with x to the 4th over 4 factorial. Right. Same thing here. If I were to find the derivative of x to the 2n plus 1, I can bring the 2n plus 1 down. This will become x to the 2n. The 2n plus 1's will cancel out. The factorial will drop down to 2n factorial. So it works for the general term. It also works for your individual terms. So there's multiple ways. Hopefully the even and odd as well as derivatives can make it a little bit easier, a couple different ways to connect these two functions. And then your interval of convergence is all real numbers. It can work for any x, so it can extend all real numbers. So negative to positive infinity, negative to positive infinity. Now, e to the x, we found the general term for e to the x, but the nice thing about connecting this with sine and cosine is basically if you combine sine and cosine together and make everything positive, you basically have your e to the x. So start with 1, then 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So it's nice. If you have sine and cosine in front of you, then e to the x is just building adding these two together, but then making everything positive. And because you see the pattern here, it should be easy for you to see, okay, I'm just make this x to the n over n factorial. I don't have to mess with these two and add those two together. I can just look at these patterns here and build my general term. And there's a mistake here. My interval convergence is also all real numbers. So if you can make that change there on your key. My interval convergence for e to the x is also all real numbers. For inverse tangent of x, there is a proof to this, and that's involving doing a geometric series for the derivative of inverse. I can show you that form if you like, but I think it's easier to just know, okay, this one, basically the pattern is look at your sign, strip away all the factorials, and you basically have your inverse tangent. So look at your sign, strip away the denominator factorial, and there's your inverse tangent. So there's the connection. And then your interval of convergence for inverse tangent is from -1 to 1. Because after this is no longer a function because it's inverse, so there is a restriction with inverse tangent. Yeah.
On the quiz, do we need to do like the building it out, or can we just put the final equation?
Just put the final equation. Wait, what do you mean building it out?
Like the x minus x.
Yes, I want you to show me exactly this. Yeah, so
Okay.
I want you to show me, it says indicate the first 4 terms, the general term, and the interval of convergence. Yeah, so I'm going to ask you for all those things. Yeah. So virtually, everything will be identical. If you know this, the only thing different is number 5. Number 5, I'm going to change that to be a different variation of the problem, but it's still going to be the same process. All right, down to 1 over 1 minus x. Now this, I just want to show you that this is in the form of a geometric series. You know how geometric series is the sum is a sub 1 over 1 minus r. So if I have that form, it's basically in that form, right? There's my a sub 1. My common ratio is just x. So if that's my common ratio, then I'm just multiplying every term with that ratio. So my first term is 1. And if I multiply that by my ratio x, it'll be plus x times the common ratio again, x squared plus x cubed plus dot, 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 x to the n. All right, so the connection with this is get it into, understand that it's basically a geometric power series. Your a sub 1 is 1 and your ratio is x. And you're just starting here and you're going to keep multiplying by x to get to the next term. And because my interval of convergence, well, I know that for a geometric series that converges, absolute value of r must be less than 1. And if absolute value of r is less than 1, that means absolute value of x has to be less than 1. And so that is between -1 and 1. So basically, you're just taking your geometric series knowledge and adapting it into your interval of convergence. Okay, back page. Now the connection with natural log of 1 minus x is the fact that this is basically coming from the derivative of 1. Sorry. It's coming from the fact that we're taking the integral of 1 over 1 minus x. Yeah. So if we know that the integral of 1 over 1 minus x, if we go through u substitution, it'll end up giving us natural log absolute value of 1 minus x. But u substitution will produce a negative. And that negative can be transferred up to be 1 minus x to the negative 1. And that's where we can flip that to make it natural log of 1 or 1 minus x. But the connection with f is the fact that it's the integral of the 1 over 1 minus x. Right. And if I can take the integral of the previous term, then I can get to my next term here. So 1 becomes x becomes x squared over 2, x squared becomes x cubed over 3, x cubed becomes x to the 4th over 4. So the connection between E and F is that F is the antiderivative version of the previous. And then your interval of convergence is from -1 to a parentheses 1, because at 1, my graph is not going to exist. Yes. Oh, I'm sorry. Okay, let me go back again. So for the previous one, we have 1 over 1 minus x. But if I take the antiderivative of 1 over 1 minus x, that will take me to use substitution, natural log of 1 minus x with a negative in front, and that will turn into this. So basically, if you understand that f is just the antiderivative of e, then just take what you built from e and then just do power rule for each term to get to the next term. And then 1 over x is basically a, we have to do a lot of rearranging, but basically we're forcing it into a geometric series. So 1 over 1 minus negative x minus 1. And if I can get in this form, this is basically the same thing as this, but now I can just think of this as my common ratio. So I'm just multiplying everything by negative x minus 1, and that will get me to my next term. And this keeps alternating signs because I have that negative as my ratio. So we're just treating the 1 over x, we're forcing it into a geometric series and then just getting it to the next term. And then natural log of x is just the integral of 1 over x. So if you can have this in front of you, just go through power rule. And if you go through power rule, there's a slight adjustment though. The 1 becomes x minus 1 just because there's a plus c that shows up, and that plus c is going to end up being minus 1. So that's the only adjustment. But if you can see that, okay, I need to make all these the same. So I'll make this x minus 1 and just go through power rule for each of the terms to get to the next term. I just wanted to make sure I went through this worksheet with you so that you can start looking at it over the weekend and then work towards getting ready for a Wednesday quiz with these 2 pages. All right, let's go back to our notes, page 22. Let's go to page 22, number 3. We're going to be building our Maclaurin series from the foundational ones that we've already built. So if I want to find the Maclaurin series for each of the following functions, I first want to build my parent. Let's build our parent function first. So I'm just going to write out the first few terms here. I know that sine of x on its own is just going to be, we know it's going to be an odd degree, and it's going to keep alternating signs. So it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. So if this is sine of x, what do you think I can do to create a sine of x squared? What adjustment do you think we can make? You have to guess. Just replace every x with what? X squared, yeah. So you're just building on top of your parent function. So every x gets replaced with x squared. This becomes x squared cubed, which is x to the 6th. This becomes x squared to the 5th, which is x to the 10th. And this becomes x to the 14th. So basically, if you have your parent function memorized, we need to, these are the type of problems that we need to be able to do. We're also going to practice writing out the general term as well. So I think that's the part that is not as fun, writing out the general term. So we know the original general term for sine of x is going to be this. And if I want to create a general term for x involving x squared, just replace the x with x squared in your general term for sine of x, and that will get you to the new general term that we need. So the x squared with the 2n plus 1 will distribute to be x to the 4n plus 2. So again, this is just based off of the general term that we've gone through on the worksheet. And we're just adapting, building our new general term from the one that we already have. Okay, number 4, what do you think we can do? What can we build out? Yeah, let's build out e to the x. Once you turn your e to the x to be a polynomial, then you just distribute that x squared through your new polynomial. And if I multiply the x squared with my general term, I get x to the n plus 2. Because if I multiply bases, I'm going to add exponents. All right, any questions here? All right, let's do this practice problem below. What is the coefficient of x to the 6 in the Taylor series about x equals 0? So it's basically saying Maclaurin series, right? Taylor series about 0 is basically Maclaurin series. For the function e to the 2x squared over 3, let's think of that as 1/2 e to the 2x squared. So we can build this out little by little, right? Let's start off with what? Yeah, let's build out e to the x, then update that e to the x, turn it into e to the 2x squared, and then multiply a 1/2 through. And then once the dust clears, then look to see, what's the coefficient that you see in front of your x6 after everything is said and done. So start with your e to the x, and then from there, see if you can build your e to the 2x squared. Oh, how do I get from? So basically, I'm just making a substitution. So you know how e to the x is here, right? So e to the 2x squared would just be replacing all these with 2x squared. It wasn't any, let's think it was any. Circumstance.
Also, I'm a little bit hazy on what the results of the test signify, like if the limit goes to infinity, I guess that means you don't include it, but I don't know what the functions are in that. So you plug 7 in, right?
Yeah.
7 in for x. Yeah, so this one would be divergent on that test, because the n squared is up top.
Yeah.
But then this would fit, how would fit divergence? Oh, right, because you're looking for values of goodness. Okay, right, so it just include, okay, yeah, cool, yeah, that's right, that's it, yeah, and this one is square root of 0, so it's testing, not testing, so, yeah.
So e to the 2x squared is just replacing every x with 2x squared because we already have a building block for each of the x. So replace every x with 2x squared, and then we can distribute the 1/2 through. And then clean everything up and see if we can figure out what coefficient is sitting in front of x to the 6th. So if I distribute 1/2 through, I'm also cleaning up my factorials there to make it easier for me to interpret. So if I distribute that 1/2 through, I really only care about that 6th term there. So 1/2 times 8/6 would be 8/12, which reduces to be 2/3, or 4/6 or 2/3. So kind of like a 3-step process here. You start off with your most basic function, and then you're just building things on top of it until you get to what they're asking for. All right, let's try one more, page 23. Can we try number 2? So number 2, what's your first building block? Sine of x, yeah. So build out the first few terms of sine of x, then update that to be sine of 3x, and then distribute the x through. Because that 2x squared is impacting your coefficient, and so there's a lot of moving parts. So I think it's easiest to just build it from scratch. I guess if you can keep a lot of things up in the air. I mean, if you can keep a lot of things, keep track of a lot of things in your head, maybe you can get to that last term. But I think it's easier to build it from scratch, even though it feels like some work. But I mean, it's also easier to double check your work if you have everything laid out in front of you. But I mean, if you find a shortcut and if you get to it, then that's fine as well. All right. Your homework, page 18 through 27, odd number problems. I'll send out a reminder over the weekend, and also start looking at the worksheet as we want to try to know that we're working towards getting ready for quiz on Wednesday with all those Maclaurin series. All right, go get your phones.
Cameras and the like sign up or whatever, and then just whatever. That's it. Yeah, and then all this noise.
Yeah, or I mean, it's gonna be one of these. 1, 2, 3, 4.
Yeah, okay.
Yeah, I can do basically any morning.
I think so. And do you want me to do the next or?
I mean, whatever helps you. Yeah, I mean, I think it helps. If you do the review, you'll come in with more detail.
That's 10.8. I 10.6 was like a normal.
10.5. So it's gonna include the alternating theory.
Okay.
So it's like one thing. So it's not even the full stack, guy. Like some things the full stack. Hold on, let me put myself right here.
11?
It's just.
7, I'm on 40 questions.
Tomorrow, 7 o'clock.
And then I'll just make the.
You're using growth rate with and like what kind of like work do you need to do? This on
But people think that like this. Trailer.
No, this one is one election. It's like one half. Yeah.
Okay, I thought you would.
I didn't buy like the growth rates. It's like. Okay,
So I
so.
hadn't over easy, but then maybe that's
One that's fun.
Okay, so if it's a one, you can't call that a polynomial.
There's the trial. The one at the trial.
Well, one over to the end.
Yeah.
Yeah.
So it's really interesting.
Right, I mean, exactly.
That's why I was like.
Yeah, to determine the
So this one.
But like.
I know the. Would it be?
Or, yes, but then you would say that.
Okay, and then it's showing, showing breaks. If you just like list out LRPE and like, just like arrows.
Yeah,
like.
I wanted to say,
And that's like.
They showed them that, they purely showed hard spot, that's. So like, the past like 5 reports that he does, but that's like.
I'm gonna ask.
Yeah, so like, it's against like, well, it's for like, nationals and like, friendly, stuff like that.
Yeah.
They wants to form the League of Nations, yes, but that is not them out.
Okay, where are you going? You dropped out. Oh, you're right. Not fair. I'm not a
Like, I'll.
I'll put the smartphones together.
I mean, how many?
Yeah, it's not like, yeah, I don't like the TV here. Yeah, we should like, we can write a memo, baby. Oh my god. Regular people can't, I just want to be like a man friend. I didn't think it was good, but you like, life is so hard, like, it's gone. Your life's not very hard.
Have a good day. Have a good weekend. Thank you.
So I want to get you.
I thought like I was creating, but this is the last one, I've done all the.
They're always supposed to be. I'm pretty sure.
Okay. Guys, I think you left your water bottle. Is that yours? Yes.
No, we're gonna simple. It's still one.
Yeah, get a bigger water bottle, bro.
Yeah, if having to buy, there's people scamming.
You don't buy them from Walmart or what?
No, actually, I think it's only marked up by like 60%.
All right, have a good weekend. See you. Bye.
All right, bye, see you later.
Bye.
I'm like, dude, they are. That's not big like that. Yes, exactly. So one has a